Hello, in this presentation I will introduce an unsupervised learning methodology for side channel analysis. First, I will briefly introduce the problem of side channel analysis and specifically power analysis attacks. Next, I will discuss our proposed unsupervised learning technique, which is based on autoencoder for feature extraction and a sensitivity analysis for leakage modeling. Finally, we'll see the experimental results and conclusions. Side channel analysis is a type of physical attack on hardware implementation of cryptographic algorithms to find the secret key. A typical cryptographic algorithm can be considered as a highly nonlinear function with unknown parameters called the secret key. A cryptanalysis or brute force attack refers to an analysis technique that reduces the search space of the secret key and possibly recovers the key given a set of input and output pairs of the algorithm. Usually, in standardized algorithms, finding the secret key by observation of the input and output is computationally infeasible. While standard algorithms are generally secure against cryptanalysis attacks, a hardware platform executing the algorithm leaks signals that have non-zero mutual information with the secret data being processed in the hardware. In side channel analysis, an attacker exploits this additional information along with the input or output of the algorithm to recover the secret key. Power analysis is a popular side channel analysis technique which assumes that the power consumption of a device is correlated with processed data. Using this relationship between data and power consumption and some structural weaknesses of a cryptographic algorithm, an attacker can recover the secret key. A typical power analysis attack finds the secret key in the following procedure. A cipher, especially for symmetric key cryptography, can be represented as multiple iterations of a permutation function. At a particular iteration called the attack location, the attacker measures the power consumption during the execution of a cipher operation. The result of this operation is called the intermediate variable, which is correlated with the measured power. The attacker calculates the value of the intermediate variable from the input or output of the algorithm and a guess for a subset of the secret key. If the calculated intermediate variable has a non-zero mutual information with the measured power, the guess is the correct key. The structural weakness of most cryptographic algorithms under side channel attack originates from the fact that the value of the intermediate variables can be calculated using only a subset of the secret key. Calculating mutual information between secret data and a limited set of power measurements usually does not result in satisfactory performance, as the mutual information involves logarithmic functions that is sensitive to noise and estimation errors. Hence, most power analysis techniques employ alternative statistics as an indirect measure for mutual information. An emerging class of power analysis techniques employ deep neural networks to establish a relationship between the power traces and secret data, or intermediate variable. A major advantage of these techniques is that different steps of a typical power analysis are implemented in a single neural network. However, for a successful attack, a proper training set is required. The training set is collected from a reference device with a known secret key which is identical to the device under attack. This is a major limitation of deep learning power analysis attacks based on supervised learning, since for a successful key recovery from a hardware implementation, an identical hardware with a known secret key is required. In this work, we introduce side channel analysis with unsupervised learning, SCAUL, that does not require prior knowledge on the leakage model nor a training set or a reference device for key recovery. The overall procedure of SCAUL is shown in this diagram. SCAUL is a methodology to evaluate the mutual information between power measurements and secret data using deep neural networks. We use an autoencoder to extract relevant features from raw power traces. Next, we estimate a leakage model from the power features using a sensitivity analysis. The leakage model is then used to cluster power features into two groups. The difference between the means of power features in the two clusters is the rank of the key candidate. The key guess that results in maximum intercluster difference is the correct key. The basic idea of autoencoders is simple. An encoder function maps the input data into an intermediate representation called the feature space. A decoder function then reconstructs the input data from the features. If the reconstruction error is small, it means that the features include most of information about the data. The parameters of the encoder and decoder functions are determined such that the loss function is minimized. The loss function in an autoencoder generally consists of an error and a regularization term. Depending on the structure of these terms, an autoencoder can be considered as a function that learns data manifold, data distribution, a denoising filter, or a dimensionality reduction algorithm. In this work, we introduce a regularized maximum likelihood autoencoder that extracts the maximum information content of the input power traces. We realize the autoencoder with LSTM neural networks. Each of the encoder and decoder is implemented with a two-layer LSTM network. The input to the encoder set at each time step is a set of samples of the power traces selected by a sliding window operation. After all samples of the power traces are processed by the encoder network, the internal state of the top layer LSTM cell represents the features of the raw power traces. The decoder LSTM network reconstructs the power traces using the internal state of the encoder. The loss function is the mean square error between the raw power traces and the reconstructed traces. Using the extracted power features, we estimate a leakage model with a sensitivity analysis. For every key candidate, we train a multi-layer perceptron MLP neural network to map the power features to the individual bits of the intermediate variable or secret data. The proposed sensitivity analysis follows similar principles as the Kramer-Rao bound. According to Kramer-Rao bound, the variations of the SCAUL function is lower bounded by the inverse of Fisher information. Assume the MLP network provides an unbiased estimate of the intermediate variable bits. By adding a small perturbation to the weights of the MLP network, the variations of the estimated output is lower bounded by the inverse of the Fisher information. As a result, if a particular output of the MLP network experiences small variations due to the perturbations, it implies that the power features include a large information content about that particular bit. Hence, the inverse of the variations at the output of the MLP network constitute the coefficients of our leakage model. We employ a SCAUL attack to recover the secret key of the Advanced Encryption Standard AES. The state of AES and its secret key have 128 bits arranged in an array of 4 by 4 bytes. At the beginning of AES encryption, the input plaintext is loaded into the state and the secret key is added to the state. Next, a nonlinear function called SBox or substitution layer operates on individual bytes of the state. We measure the power consumption during the execution of SBox operations. The intermediate variable is the result of the SBox operation, which is correlated with the power consumptions. The power consumption of AES at the beginning of encryption or decryption includes the power traces corresponding to 16 SBox operations on the 16 bytes of the state. We separate the power traces of individual SBoxes and feed them to the LSTM autoencoder for feature extraction. The power trace measured during one SBox operation of our AES implementation on Artix-7 FPGA is shown in the top left figure. The reconstructed power trace by the autoencoder is also shown in the figure. We observe that the reconstructed trace follow the main features of the raw trace while high-frequency variations are filtered. This demonstrates that the autoencoder features include most of the information content of the measurements. The power features extracted by the autoencoder from power measurements during multiple encryptions is shown in the bottom left figure. The variations at the output of the MLP network due to small perturbations in its weights is shown in the right figure. The smaller variations of low-order terms implies that the power consumption in this implementation is mainly correlated with the low-order function of the intermediate variable bits. The results of a SCAUL attack is in recovering the secret key of AES from the power measurements during execution on an Artix-7 FPGA is shown in this slide. The results of a classical differential power analysis DPA attack is also shown for comparison. According to the top left figure, a DPA attack which assumes the power measurements are correlated with the Hamming weight of the intermediate variable requires at least 17,000 traces to identify the correct key. As shown in the bottom left figure, when we replace the raw power traces in the DPA attack with the autoencoder features, we can recover the secret key with only 1,600 measurements. This is an order of magnitude improvement in attack efficiency. This result demonstrates that not only the autoencoder extracts most information about the secret data from the measurements, but it also reduces the effect of noise. The right figure shows the result of a SCAUL attack in which the leakage model is estimated from the measurements. It is observed that SCAUL is able to identify a proper leakage model and find the correct key with only 3,700 traces, which is still much smaller than the classical model-based DPA attack. The results of a SCAUL attack with misaligned traces are shown here. We add an uncertainty in the timing of power measurements that is equal to 20% of a clock cycle. According to the top left figure, the DPA attack fails to find the correct key with more than 20,000 traces. This is a major limitation of classical power analysis techniques, which require a set of perfectly aligned measurements. However, as shown in the bottom left figure, a DPA attack with the autoencoder features identifies the correct key with less than 8,500 traces. This result implies that the autoencoder is able to extract information about secret data even if the measurements are not aligned, and the information is distributed over random samples of power traces. Finally, the results of the SCAUL attack with misaligned traces is shown in the right figure. By collecting nearly 12,000 traces with a timing uncertainty equal to 20% of a clock cycle, SCAUL is still able to recover the correct key. In summary, side channel analysis is basically the problem of finding the mutual information between a set of measurements such as power consumption from a hardware platform executing a cryptographic algorithm and the secret data. We introduced a SCAUL that employs unsupervised learning to evaluate the mutual information amid model uncertainties. We demonstrated that SCAUL is able to identify the correct key of the AES algorithm using power measurements from an FPGA implementation without requiring the leakage model. Further, SCAUL is successful even with uncertainties in timing of measurements in which the power traces are not perfectly aligned. Thank you for your attention.